not-for-profit organization providing our members with credible information and resources for renewable energy and now energy systems integration decisions, peer-to-peer networking, knowledge sharing, and professional education experiences. Last week, we finished up our spring technical workshop in Tucson, and our next activity is going to be the forecasting workshop in St. Paul, which you're all invited to attend. This is our 10th annual, and it's been quite a successful and quite a popular workshop over the years. There's really nothing else quite like it anywhere, mixing meteorology with power systems engineering and operations. And if you're new to ESIG, I strongly encourage you to check it out and follow up with us if you like what you see. I don't think you'll be sorry if you do. You can find us at our new web address, www.esig.energy. Okay, before we get started, just a few little logistical matters. Phones are all on mute. They'll stay on mute. And we'll ask you to use the question and answer box in the lower right-hand corner of your screen to submit questions, and we'll save 10 or 15 minutes at the end for the Q&A, and plan to wrap it up at the top of the hour. So I'd like to go ahead and introduce our webinar presenter, Derek Stenclik, Manager of Power Systems Strategy Team in the Power Economics Practice Area at GE Energy Consulting. Derek's been there since 2011. And in this role, he's primarily responsible for studies and analysis using production cost and reliability models for global economic and power system consulting. His areas of expertise include electric power markets, wind and solar integration, and energy storage. Derek's most recent projects involve wind and solar integration studies with specific focus on small island systems where integration challenges are more demanding. In this role, he has provided extensive modeling and consulting support for studies evaluating the impact of high renewable penetration on system operations, reliability, and economics. He's currently the project manager for ongoing renewable integration consulting in Hawaii, which leads the United States in solar PV adoption. So Derek, I'm going to go ahead and turn it over to you.
All right, thank you very much, Charlie, and thank you all for joining. I hope you find this webinar interesting and you learn something, and hopefully with some of the questions that we get at the end, I can learn a little bit more about what all of you are thinking about and with respect to energy storage. I know it's quickly moving in the industry. As a consultant, it's exciting getting to see how customers are evaluating storage, how grids are starting to integrate it, but there's a lot of uncertainty, a lot of unknowns still in the space. The industry is quite a bit of buzz, and it's at times tough to weed out some of the hype with some of the real practical economic and use cases for storage. So what I'm going to try to do over this presentation is give you my perspective of where I see kind of the future role of energy storage for renewable integration and really understand the different energy storage value streams. Again, it's my perspective, not necessarily this, the corporate view for the rest of GE or even within energy consulting. I'm really just going to share some of the lessons learned that I've seen as we've done some of this consulting work for our clients across the industry. So with that, I'll give you a little bit of background. I have a slide here about the energy consulting business, and really more to just set the stage. We are a consulting group that's independent from the different product lines across GE. So there's been a lot of press releases recently in the news from GE about the business's energy storage product line. I'm not going to touch on those topics or the technology in particular, but instead use some of the experience that our consulting group has had doing system studies for clients across the industry. If you do want to follow up with specific questions on the technology, I can point you in the right direction. But today, I'm going to focus really on the systems integration piece, as Charlie was alluding to in the beginning. And really where that systems integration approach comes from, or where it stems from, is a long history of doing renewable integration studies really across North America and globally. So as many of you are aware, ESIG has been involved in a lot of the wind and solar integration studies that we've participated in as well. So really working with grid operators across North America, Europe, Australia, India, and in the Caribbean, looking at how does the system integrate additional wind and solar, and what mitigations need to be taken to ensure that's done economically, reliably, and while maintaining grid stability. And what that's always shown, all this work has shown, is there's never really a hard limit to renewable integration. It's just a matter of bringing on new technologies and new ways of operating the system that may differ from historical operations. So just wanted to show this slide as really the context of what framed my mind and how I think about energy storage as one of many tools for renewable integration, and we'll touch on that more as I walk through the presentation. And then most recently, like we've seen kind of across the industry, we've started to do more work on specifically in the energy storage space, both as a piece of renewable integration studies, but also as standalone projects. So just wanted to touch quickly on where some of the projects we've been involved over the past year that I think have also framed some of the insights that I'm going to provide. So a couple of the slides show directly some of the results of these studies. Other ones have just kind of guided my thinking in some of the ways we're thinking about storage here at GE Energy Consulting. So kind of kicking off with the energy storage review in particular, you know, there's been a lot of hype, as you all know, in the industry. It seems like every day when you open up, you know, the news, the industry press, there's a new headline. So I've got some of the headlines that have really, you know, shaken up the industry over there on the right. Obviously, you have the large 100 megawatt plus battery storage project in South Australia. You know, it seems like each company is starting to either develop energy storage internally or looking to acquire other companies or partner, as in case in Siemens and AES. And we're really starting to see regulators latch on to storage as an emerging technology, and one that should be pursued in a very similar way that regulators and policymakers pushed for renewables. So we're starting to see lawmakers and regulators push for mandates on installed energy storage. So have there at the top the states that have implemented some form of energy storage mandate. So Arizona, California, Massachusetts, Nevada, New York, and Oregon all have storage mandates in total. They add up to about 6 gigawatts across the United States, and there's active proceedings in 13 others. So I think a real trend we've seen is regulators and policymakers getting into the driver's seat of the electric system transformation and starting to really identify, in particular, energy storage and battery energy storage as a tool that needs to be really piloted, and there's a role of government to facilitate the integration into the grid. So for better or worse, that's a trend that we're seeing really across the industry. Recently, FERC orders, I'll touch on FERC Order 841 later, but that's really setting the stage for broad-scale RTO ISO implementation of storage. And then, you know, other consultants along with energy consulting. So Brattle just issued a study looking at, you know, how could the energy storage market evolve to be 50 gigawatts in size and of capacity. So a lot of hype there. And I have at the bottom here, 78%, you know, utility dive survey, 78% of utility professionals expect utility scale storage to increase moderately or significantly on their systems. So, like I said, the industry at large really starting to change its thinking as historically energy storage being a niche technology and used sparingly to one that's really coming at the forefront, and a lot of open questions about what the role of energy storage is going to be and how big is it going to be. So I'll try to answer some of those questions over the next few slides here as best as I can, as I see it now. So this is a slide I brought in here just to ground the conversation a little bit more, because while battery energy storage prices have come down quite a bit and the technology has advanced dramatically, storage in general is not necessarily a new technology on the grid. It's something that has been really a large part of the power system for decades. And you know, the industry at large has many, many years of experience on how energy storage can provide a variety of services, whether it's shifting energy from one time period to another, providing ancillary services like regulation or black start capability. You know, historically, that's been done predominantly through hydro pump storage. So I understand that that's a very different type of technology, but the use cases and some of the applications are very similar between the hydro pump storage that we've seen in the past and some of the new installations of the battery storage that we're seeing now. So I think there's a lot of lessons learned that we can take from some of that work and some of the previous analysis and really frame the conversation that while battery energy storage is now much cheaper than it has always been, we got to ground ourselves and also understand that it's not necessarily a service that the grid has never had before. Another thing to kind of ground ourselves is, you know, going back to that renewable integration slide that showed the GE experience. There's been a lot of integration studies across the industry, either done by GE or NREL or others, that have really been consistent in the outlook on energy storage, and that's there's really not an inherent economic or physical need for energy storage at renewable penetration up to about 40% of annual load. And that number is it's a gray number. There's really no hard and fast rule here, but the big takeaway is, you know, energy storage at some point will be required for additional variable renewable integration, but that point is much higher than points that we've reached today. So in terms of the barriers or the obstacles of further renewable integration on the grid, we are not at a point in most places where battery storage is required to move forward. There may be places where it's economic, but in terms of a roadblock or a barrier to further, you know, wind and solar integration, we're not there. Again, in parentheses there may be some small remote or island power systems where that number is lower. It might become necessary much sooner, but again, for the broad grid, we have a long way to go in terms of how much wind and solar we can integrate into the grid before we start requiring new energy storage. So talk a little bit about the rapid evolution of the battery energy storage industry. Prices are absolutely plummeting. It's, you know, I put down a few numbers there that are really my best guess after, you know, reading a lot of work that's out there in the industry, a lot of other reports. Essentially, $250 per kilowatt hour for the actual battery cells, and then when you start talking about an installed plant, you know, 4-hour duration, we're looking at about $375 per kilowatt hour. That's dramatically lower than even what it was last year. And it's almost to the point where I hesitate putting numbers on a slide because I know by the time I present it, it could be out of date. So a lot of movement there in terms of pricing. I think there's a lot of potential cost reductions that are still going to come. And the one thing that is coming out for sure is lithium ions becoming a clear winner, at least for now. And I have a pie chart there on the right that shows the different cell chemistries of battery storage systems. This is really for everything in the US that's been installed to date to the end of 2017. And I think if you looked at the last year in particular, lithium ion would be an even larger percentage of the most recent installations. And really there's been a lot of enthusiastic deployment. The projects that have been implemented are getting a lot of press. A lot of folks are keeping track of these projects very closely, and I think there's a lot of enthusiasm about being a first mover. So I think businesses and either both the OEMs and the developers are all really trying to push to be a first mover in this space, see what we can learn from these applications, and see how well we can scale it to the rest of the industry. And I think at this point, the big open question is, what's the sweet spot? What's the application that we want to start using for these different battery technologies? There's a lot of different services that they can provide, which I'll be getting into, but what do we want to focus on, or what's the near-term use case? And so moving on to the next slide here, I wanted to just highlight some of the recent battery energy storage deployments that have really made the press across the industry. And I'll start kind of left to right. KIEC, Kauai Island Utility Co-op, really 2 solar plus storage systems going in there. And I've colored this map so that the coloring is, the orange states and regions are ones where it's really largely been a solar plus storage shift. Basically a 4-hour duration battery tied directly to an existing solar plant or a new solar plant. Whereas the blue regions specific to, 1 or potentially 2 ancillary services, so fast frequency response or regulation. And then, green, a little bit hard combination of the 2 there. So California, we know, has one of the largest state mandates for new energy storage. We've seen applications there ranging from capacity peaker replacements to solar plus storage shifts to even hybrid systems linking energy storage with conventional gas peakers so that they can participate in spinning reserve markets. So a lot of various use cases there. Arizona Public Service and Florida Power and Light, 2 probably most recent announcements there for 4-hour or so duration solar plus storage projects, really capturing the idea of shifting solar energy from the middle of the day and start being peak renewable sources of energy. And really, I think driving a lot of that investment is the renewable targets, and specifically, ones being discussed in Arizona about peak hour renewable targets, along with the solar ITC and having the ability to get investment tax credit incentives on storage capital as long as it's tied directly to a solar plant and uses the energy produced by that solar plant. In the blue here in PJM, those largely going back to the 2015 timeframe, a lot of investment on the regulation market there. So looking at specifically regulation assets, there's been quite a few changes to market rules there in PJM related to the how energy storage or specifically energy limited resources can provide that. So kind of an open question of how that progresses in the future. And then in National Grid in the UK and specifically South Australia in AMO, places where really fast contingency reserve, fast frequency response assets are being deployed, again, because those are unique, lower inertia power systems, or places where there's been high renewable penetration and potentially a risk of frequency response, as we saw with the South Australia blackout a couple of years ago. So just an overview, obviously not all of the battery applications, but just kind of wanted to walk through the different use cases that we're seeing. They are varied and they change depending on where we are and what the power system looks like. We wanted to touch on a few of those and really to set up the discussion for the rest of the conversation today. So the question, I to some extent already answered this earlier, but is energy storage required for renewable integration? And the chart on the left here is your classic duck curve, where net load is decreasing and getting lower and lower in the middle of the day due to the increase in solar generation. And the peaks are, to some extent, getting higher. So the logical application of battery storage has been, or a lot of people have been talking about, energy shifting. So whether it's storage or demand response or load shifting, but basically charging the batteries in the middle of the day to discharge during evening peak. And while eventually that may be necessary, what we've seen in all of the integration studies we've done is that's really not economic until very high penetrations, much higher than the ones we're seeing today. So even in places like California or even in places like Hawaii, which have a dramatic duck curve, the best use case isn't necessarily shifting from one time period to another with a high energy, low power battery application. In the near term, what we've seen is short duration regulation storage, again, or demand response, can provide kind of that increased flexibility over minutes So a lot of, whether it's fast frequency response or regulation reserves, some of the ancillary service markets or power system requirements are really where we see the more near-term applications of energy storage, specifically when it comes to renewable integration. We'll get into that in a little more. So, going back to the question about whether energy storage is required, and one of the reasons that we've seen in a lot of the integration studies we've done that it's not necessary until very high penetration is there's still a lot of flexibility across the power system. So battery energy storage, often I've heard it referred to as the Swiss Army knife of the power grid, because it can provide a lot of different services. You can use it for energy shifting, for regulations, for synthetic inertia, or voltage control. There's a lot of different use cases, but what I would say to the Swiss Army knife analogy is the grid already has a toolbox, right? And there's already a lot of tools and capabilities already inherent in the system, one of them being the ability to add energy storage. So when we talk about the existing synchronous generation, getting faster ramp rates and faster startup shutdown cycles and lower stable operating points, we've seen very effective mitigations to integrating more wind and solar on the system. Also, the ability to switch between generation mode and potentially synchronous condenser mode, either via clutch, so that it can be done kind of seamlessly back and forth between the two, or as we start to see aging infrastructure or fossil generation being retired, the potential to convert into synchronous condensers to provide some of the reactive power support on the grid. In terms of the renewables themselves, the wind and solar, the inverters are getting much more sophisticated so that a lot of the ancillary services, the grid services that storage can provide, can also be provided by the renewables themselves. So regulation, fast frequency response directly from the wind and solar is certainly a technical capability. In fact, the speed of response for a lot of those resources are even faster than conventional thermal generators. But there is an economic cost of doing some of those, right? There's an opportunity cost of curtailing or wind or solar to provide some of those reserves. But I think, having that economics discussion of if reserves are going to be binding only a few hours of the year during very rare operating conditions, it may be worth that foregone opportunity cost of curtailing some of the renewables to provide a grid service if the alternative is investing in a new battery plant, which can be much more costly. So again, using the tools and the systems that we have already on the grid, oftentimes we've seen in the integration studies can be very impactful mitigations. And then I think there's also a lot of untapped potential on the flexible loads, whether it's using time of use or real-time pricing to shift the duck curve around a bit, or having controllable loads or autonomous loads that can be turned off to provide fast frequency response or regulation. I think there's a lot of potential. There's inherently a lot of storage already out there in our loads, and making sure that we're capturing that flexibility as well is important. And then lastly, energy storage, I'm not here to doubt that it's an incredibly useful tool to the grid. It can provide various different applications. Just wanted to set the context that it's one of many tools that we have at our disposal. And as we're going through, whether it's a wind and solar integration study or if it's an integrated resource plan for a utility, we want to make sure we're looking across that value network and making sure we're getting all the flexibility we can from the resources that we have. So touched on this a little bit already, but there's, in the simplest context, there's really two primary use cases. There's the energy shifting example of energy storage, and then there's the ancillary service, or the grid service use case. And so in most places, we haven't seen a huge need to shift energy from one time period to the other, as you see on the left there. But instead using it for grid service like ramp rate control or regulation and load following, we've seen as more near-term applications on the grid. So, storage use as fast frequency response, regulation reserves, load following and ramping capability, black start, voltage support, and potentially, some T&D upgrade deferral. So can we, rather than upgrade a transmission substation or add a new transmission line or distribution feeder, can we augment what's already there with a little bit of energy storage and defer an upgrade? There's a lot of talk in the industry about using storage for that. When it comes down to it, finding the specific use cases is challenging. So I think there's a lot of potential there, but it's going to take a lot of good engineering analysis to really identify where that's the most economic. So I'll take an example from some of the work that we're doing in Hawaii now and talk about this concept of shifting or not shifting the energy. Should we look at storage to shift energy from the middle of the day to the evening peak, or should we use it for grid services? And Hawaii is a great example because it's an island system with quite a bit of solar penetration. So really leading the nation on a per capita or size of the system basis in distributed solar PV adoption. Just to give you some context, Oahu, where this study was performed, has about 500 megawatts of distributed PV on a system that has a midday load, gross load of about 1,000 megawatts. Just to give you some context, if it's a clear solar day, we could be approaching 40–50% of system load being provided just by rooftop PV. And then on top of that, 150 megawatts of new utility scale solar coming on the system. And so we did analysis looking out to 2030 with even more solar on the system. What's the appropriate use case of storage, and what's the appropriate size? So we looked at, you can see, I think it was 14 different configurations of battery storage systems that range in their power rating here on the left from 25 megawatts to 200 megawatts. And duration, so duration of half an hour up to 4 hours. And so you can see on a megawatt hour basis, we range from 25 megawatt hours to 400 megawatt hours. And we wanted to get a sense of, just looking at some of the trends, what did we learn from that? And you can see here, this is a chart that shows when we add storage to the system, what increases in generation off to the right of the chart in solid, and what decreases generation, and that's shaded here in the hash mark. So in general, because the system had a significant amount of renewable curtailment, we saw solar and wind increase generation because it was being, solar or the storage, in some cases shifted energy from one time to another, and in other cases was there to provide a grid service that freed up space on the grid for the wind and solar to be added. And then on the left, really the conventional steam oil generators being the ones displaced the most. But really, the big thing that came out of this, if we want to just focus here on the 100 megawatt hour blocks here, there's 4 different configurations that range on the bottom here, low power, high energy, 4-hour BESS, up to a high power, low energy. And you can actually see that there's a more significant increase in wind and solar with the high power, low energy battery, which at first was counterintuitive because there's less capability to shift the energy necessarily from middle of the day to evening peak. And what we saw there was by having a high power asset, it was able to provide reserves like regulation reserves and fast frequency response that allowed other conventional generators to turn offline in the middle of the day. So not only are you able to shift from one time period to another, but more importantly, we're actually able to free up space on the grid in the middle of the day when the solar output is highest. And so that was really a key finding, that a reserve asset can be a large asset to increase wind and solar on the grid. And you don't necessarily, the best use case isn't necessarily shifting from one time period to another to reduce curtailment. You can find more information. I have a link to the full study there. This is just one excerpt that is available online. But we looked at a few different applications and tried to tease out from reserve assets to energy shifting assets, what's the most economic? And again, the applicability to the rest of the industry, I don't want to say it's directly applicable everywhere because this is a unique system. It is an island system where reserves are more valuable, but just a very interesting finding, and I think something that should be evaluated in other places as well. So another example from the ongoing analysis there in Hawaii is a question of can storage replace conventional peakers? I think that's really one of the next use cases that we've heard a lot of discussion about in the industry. And I think the answer is there's some risk to some conventional peakers, but not all. And the reason for that is the same way capacity value, and here I'm speaking of resource adequacy, so the ability for a resource to displace a conventional firm generator during all time periods, saturates for energy storage very similar in concept to the way capacity value for solar or wind saturates with increasing penetration. And I tried to illustrate here, and admittedly this is somewhat of a cartoon, but if you look at a net load duration curve here of the system, you can see that to decrease the 100 megawatts provide 100 megawatts of firm capacity for that first 100 megawatts only really requires 266 hours of a full year. To get the next 100 megawatts of peak load, you need about almost 1,000. And then the next 100 after that, you need over 2,000. And so you can see there's a saturation effect of how much how much the resource needs to be available to displace firm capacity. And on the right here, illustrate kind of a similar concept on one day of operation, where again, the first 100 megawatts may only need to be available for 2 hours, but as you start to increase the capacity of the storage on the system, it needs to be available for a longer period of time to provide firm capacity capabilities. And you can see this is just showing when you would discharge. Obviously, with the storage, you need to charge at other times, so that would increase the net load during other periods, and you start to really saturate the ability for the storage to provide some of that firm capacity. Now, one thing we've seen here is that's largely dependent on the amount of solar on the system. There's a recent report came out a week or two ago from NREL and Paul Denholm and crew about the capacity value of storage really being driven by the amount of solar on the system. And so with increasing solar, you get a little bit more capability from the storage as a capacity resource. I think where you run into limits there is, one, there's going to be some cloudy days on the system, and now your system risk, where historically most of the system risk was during peak load days, you get to a point where the system risk is driven by your cloudy days. And then there's also a saturation point because you need to charge that storage during other time periods in order to discharge it in others. So we went one step further in the analysis we were doing there in Hawaii, and this is preliminary, just kind of coming out now. We looked at, as we started to increase the storage capacity on the system, what's the capacity value it provides? And capacity value here is really to decrease the loss of load expectation on the system and be available at times of need, right? And so we can see an interesting trend is it actually increases at first, and this is showing that there is some a certain threshold of capacity that would be required to meet some of the loss of load expectation on the system. And so it actually increases there for a little bit and then starts to decrease and saturate. So what it's showing is, for a 4-hour system, maybe 75% capacity value, again, the ability to offset the conventional firm generator, and then it starts to diminish so that, and again, this is the average capacity value of all the storage evaluated, saturates to around 40%. And you can see there's a range there, depending on how many hours you have of the storage. But, we see the same trend, that capacity value starts to diminish with increasing penetration. Another interesting finding we see is for the 2-hour storage, the shorter duration storage, typically the capacity requirements in most ISOs, RTOs, and even vertically integrated utilities, the capacity requirement says a resource has to be available for at least 4 hours. And what this shows is even a shorter duration storage or demand response application could provide some capacity value. Obviously, it's a little bit less, but if you have energy limited resources, you want to use them to whatever extent you can. So I think it becomes a question of how do you monetize, or how do you pay for performance for longer duration assets versus making sure if you have a resource available, use it even if it's not the full, doesn't have a full 4-hour capability. So what's the role of power markets? There's, again, a lot of different services that storage can provide, going back to the Swiss Army knife analogy. I've got them listed out here with energy and capacity, ancillary services, T&D, deferral, and then some end-use kind of behind-the-meter applications. And you can see the shading. It shows where this is a monetary value that can be, is currently valued in deregulated markets. So we have our capacity and energy shifting, and then some of the ancillary services. A few places where it's being proposed, whether or not there's a need for ramping capability or ramping products out there, and then fast frequency response, something that's emerging more and more in the industry. We've seen, now markets in Ireland, which have a FFR or market. There's one in New Zealand, the UK, and we're seeing proposals in places like ERCOT in Hawaii and other places. I think that's kind of an evolution that we'll see continue. And then when it comes to the T&D space, it's really an open space. I think there's a lot of value that storage can provide. It's going to be a challenge, though, of how we monetize that and how we value that across the different markets and ISOs. So they can provide a broad array of system benefits. Only some can be monetized. I think the recent FERC Order 841, that's going to start to formalize how energy storage should participate in these wholesale power markets and how they can be treated on a similar playing field, similar footing as conventional resources, but also understanding that they are different. They have energy limits associated with them. So just a quick note on FERC Order 841. If you haven't seen it already, I suggest do some reading up on it. It's very interesting. I think we can expect quite a few tariff changes across the different ISOs here in North America. Really requiring ISOs, RTOs to revise the tariff to allow storage to participate in any markets that they're technically capable of providing. So ensure they're eligible for capacity, energy, and ancillary services based on the technical requirements. Ensure that electric storage can be dispatched and set the wholesale market price, either as a buyer or a seller. So there's some open questions before about what the LMP would be for storage assets, and particularly here, ensuring that if the storage is purchasing power, it's doing so at the wholesale LMP rate, not the retail rate of electricity. And finally, minimum size requirement, fairly small here, 100 kilowatts, making sure that the ability, one of the great parts of energy storage is, while there are some economies of scale going from relatively small systems up to larger ones, it's nowhere near the same extent as kind of conventional generation. So I think there's a lot of opportunity of this kind of distributility mindset where you have larger projects, maybe on the order of 5-10 megawatts of storage, that can be distributed across the system at the substation level and the distribution feeder level, and really target the locations where storage can be deployed. So another trend that I'm seeing quite a bit in the industry now is hybrid projects. And I think really there's a few reasons why that's occurring, but ultimately the initial storage deployments really need to benefit from creative thinking, and hybridizing storage with other conventional technologies or renewable technologies is a great way to start. So we've seen a lot of deployment with solar plus storage, wind, I think wind plus storage, there's a lot of opportunity there. We've seen a couple pilot projects in that space. And then even conventional gas technologies. So most recently, our group's been involved in hybrid projects with aeroderivative gas turbines augmented with battery storage, really allowing very short duration battery storage, allowing a conventional gas peaker to provide spinning reserve even when the asset's off. So the battery storage is providing that initial spinning reserve and just for the time period it takes for a conventional gas peaker to start up. So again, a unique application there that I think is offered by hybrid technologies. So other reasons, I think this is going to be a continuing trend. The first one, somewhat obvious, the tax incentives. So the ability to couple energy storage with solar plants and benefit from the solar investment tax credit, basically a 30% CapEx benefit there. If it's attached to a solar plant, I believe 70% of the charging energy for the battery has to be provided by the solar plant in order to participate or to be eligible for the ITC. I could be a little bit off on that exact percentage. One of the big benefits I see is simplified procurement, financing, and PPA construct, whereas it's very difficult for storage to go out as a merchant facility and provide either ancillary services or even energy arbitrage, but when it's tied to another project, it just facilitates some of the negotiations and some of the procurement for the utilities and the financing with the banks that I think makes it a little bit easier, especially as we start to move from pilot projects into the field. I think that opens up the door to streamlining that process across other technologies. There's the capability to certainly share AC infrastructure, so the point of interconnection, the transmission substation, but also potentially the DC components, so coupling, sharing the inverters across solar, wind, and battery technologies is possible. And then integrated plant controllers, so having storage operations optimize the entire plant. So we know there's degradation on the storage, and when we're using storage, we know there's some degradation specifically when it comes to wind on some of the movable parts. Can we use the two technologies together to really optimize the performance of each other and limit the degradation? Obviously, siting and interconnection benefits, potentially not having to go through a full another round of interconnection analyses if we're siting at the same POI. And I think kind of going back to the gas technology hybrid, the ability for one resource to access new revenue streams that it wasn't able to before is a good example. So certainly a trend I think will continue. And that brings me to my last slide, kind of right on time here. There's no doubt that energy storage can play an integral role in the future power grid. There's a few things that I try to remind either clients or folks I speak with in the industry. When we're talking about regulations and markets, I always view them that we should target those for tailor them for desired results. So minimum capacity targets are good if we just want to get deployments out there in the field, but they may not necessarily get the grid services that we want from them if there's no clear market signal. So I always like to tailor either market rules or regulations in a technology neutral way. If we see a need for something like fast frequency response, let's tailor a market around that and allow all resources to participate in that market. And if battery storage is has some technical preference there, it should be rewarded for it. So I think being careful about just putting blind targets versus making sure we're putting the right incentives to value what we want out of the storage is important. Again, I touched on the need to be technology agnostic. So going back to the point that storage is one form of grid flexibility, but we need to remember there's other ones out there. And it's really the way I view storage and really any technology, it's part of a broad portfolio that a grid operator or utility has at their disposal. You know, whenever we talk about one technology in isolation as kind of the future, I always think we need to take a step back and really look at this as a broad resource mix. And this is one tool of many that's out there for our disposal. And then, you know, touching on the last slide there, there's going to be a diverse mix of storage projects. And I think that hybridization will continue. But one of the risks I see with hybrid projects is I want to make sure the industry knows that storage is not necessarily required for new renewables. I don't want to see it as a roadblock that something says, you know, wind plant or solar plant without storage can't be interconnected into the grid. So that's something I want to make sure we avoid, is storage can provide additional services if people want that on the system. And then when it comes, again, with the hybrid projects, I want to make sure the storage is being optimized or operated to ensure, you know, system benefits and make sure it's being done not just for an individual plant need, but for the system needs, and particularly there for, you know, ramping reserves. If, you know, the last thing you'd want if the solar is dropping on one plant and the storage is increasing, but for all the other solar plants, the output is increasing. You don't want the storage to be doing kind of counterintuitive things to the rest of the system. So again, you know, make sure that the storage is optimized and operated at the system level, not just the individual plant needs. And with that, I'll kind of hand it over to questions. You know, I know we're running short on time here, so I have my contact information on the bottom right if you want to reach out. There's also, again, some reports and things like that that I spoke about earlier in the presentation can be found on our website. So with that, I'll throw it back over to Charlie, and he'll field the questions from the group.
Okay, thank you, Derek. Done a good job of managing the time. We've still got about 10 minutes left. If anybody has any additional questions, go ahead and add them to the Q&A box. I think I'm going to start towards the end because of the last comment that you made on the last slide. Derek, we have a question here saying that it's better to operate storage for the systems, not just for the individual plant needs. I think that was the last point on your last slide. How do you account for the emerging popularity of the combined solar storage plant, you know, the hybrid that you also talked about? It makes no sense to me. How about you? So put you on the spot there.
Yeah, I think going back, really where I see the hybrid, and this, admittedly, this is something I had to grapple with for quite a bit myself. You know, why should we combine these technologies? And going back to, you know, that earlier slide there, what I think, I mean, obviously there's the policy incentive that, you know, we'll ignore for now. I think that's a large part of why they're coming together. But the biggest benefit I see in the long run is this simplified procurement strategy. And where I think we've seen a lot of customer traction is there's really a soft cost with a utility that needs to go to their regulator for approval on a project. Being able to combine these technologies and bring it forward as one plant, you know, one PPA, there's decreased risk there. There's kind of going through this procurement process is streamlined. I think, you know, as somebody like with an economist background, sometimes I, you know, forget about the reality of developing projects and bringing new projects online. I forget that, you know, in a perfect world, maybe everything is separate and there's a lot of different actors and we have a bunch of small battery providers, you know, providing small plants. But I think in reality, the procurement, the financing, the PPAs are a large part of the industry that we can't just ignore. So the ability to bring hybrid projects together, whether it's batteries and solar, or it's solar and wind, or, you know, we're even seeing a lot of uptick in reciprocating engines and solar being kind of bid in together. I think that's a trend we'll see continue. And then, you know, I think the shared AC infrastructure, DC components, you know, even if you can only save 5–10% of CapEx or, you know, by sharing some of the transmission interconnection, it's a really competitive market out there when it comes to solar, wind, batteries. I mean, prices are lower than we've ever seen them. So 5–10%, even a 5% cost savings on the CapEx can be the difference maker in a project. So while it's, potential to save on some of the transmission interconnection or the development costs seems like a trivial amount, it's quite a bit when you start looking at how competitive these projects have gotten. So again, something that I was grappling with, admittedly, over the last year or so on why are these plants hybridizing. I guess what I would like to see is just make sure that if there is a hybrid project, it's able to play in all of the different markets to provide a variety of different services. It's not just there to shift energy from the middle of the day to the evening peak, because that may not be the best use case in all applications.
Let me follow up that question with another question, Derek, on the gas turbine battery hybrid versus the PV battery hybrid. I've seen hype in the last couple months saying that the cost of PV is so low now that the PV battery hybrid is going to basically foreclose the market for gas turbines, even gas turbines with batteries. What's your view on that? Where's what's the pluses and minuses of those two sides of the coin?
Yeah, I can tell you it's been a very interesting time to be at GE, having both the gas turbine product line and getting to see folks working there and the solar storage play. I think what I see there is certainly with the prices we've seen out of solar plus storage, if those continue, especially if they continue after the ITC expires, it's going to add pressure to the conventional gas turbine, especially new orders. There's certainly going to be pressure there. What I would to combat that, going back to the capacity value analysis I was showing, there's a saturation effect, right, where a solar plus storage project may be very competitive for those first few gas peakers on the system. There's a very open question on how many gas turbines can be displaced. I think in the end, in the long run, it's going to be a diverse portfolio across the system, so a really balanced energy resource mix. Some of the work that we're doing in Hawaii to see, well, can we get to a point where solar plus storage is really in it of itself could be a reliable, main component of the grid. I think there's a lot more understanding that needs to be done there of, what happens if there's multiple days in a row of clouds and inclement weather? What happens if we have a low solar year and things like that? So I think overall, yes, certainly for the first few gas peakers, there's going to be a lot of competition there, but I really see a diverse resource mix. I still see gas as having a role in the power system, at least for the foreseeable future.
Here's a related question, Derek, related to the, I think the hybrid solar battery plant. What about providing a product to provide ramping, as in CAISO?
Yep, absolutely. So going back to this slide of where the role of power markets, I kind of touched a little bit more on the fast frequency response, but the ramping reserve is certainly something that we've seen either, CAISO has the product there, and I think other ISOs are really starting to consider whether that's going to be needed. So certainly, again, if it's something, if the analysis shows from both a reliability and economics perspective that additional ramping capability is needed on the system, my preference would be to have a market product that values that service. And then if the best way to provide it is, adding solar plus storage hybrids, then that's, ideally we can chase those opportunities. But I think, looking at CAISO, for an example, one way to get that is the hybrid project. Another way is to increase the balancing area footprint. So looking at the energy imbalance market to bring in a more diverse group of resources, a larger pool of resources, more geographically dispersed. I think that's another way to combat things like ramping issues or even the energy shifting issues we're seeing in California.
Okay, here's a little different topic. Probably an opportunity to say a little bit more and help clear up some misunderstandings on synthetic inertia. And the question is, can advanced inverters really provide synthetic inertia? I thought real power injection is required. So maybe a little background.
So, yeah, absolutely. So in terms of the advanced inverters, yes, for dynamic frequency response, as frequency declines after a contingency event, whether you use, I tend not to use synchronous inertia and prefer fast frequency response. So basically the ability to inject real power after a contingency event from a power electronic resource, whether it's wind, solar, or battery. You are correct that if you have a solar plant on its own, unless it's being curtailed, there's no way to rapidly inject more power if it's already at max output. So to provide that service, you would need to either be curtailing your resource or augment it with storage. Now, where I was going before is if we look at a high renewable future, we have to expect there's going to be curtailment during some times. Obviously, we want to minimize it to whatever extent we can, but in the most critical periods, there will be some form of curtailment. I want to make sure we use that most effectively and make sure that we can provide something like fast frequency response after a contingency event from the curtailed renewables. The other one with wind, the ability to provide fast frequency response via wind inertia, because there actually is a rotating mast, although it's decoupled from the AC system, there is an ability to provide a very short burst of energy following a frequency decline on the order of magnitude of a few seconds of response, even if the wind turbine was at max output. So that's kind of a characteristic specific to wind, but ability to provide FFR there just for a few seconds, but ultimately in a low inertia environment that can do a lot of help to restore a system.
Good explanation. Let me ask one last question, then we're going to have to wrap it up. We've got about 2 minutes left. What do you make of some of the recent PPA bids, i.e. extremely low PPA prices versus actual installed costs? Is it all subsidies or is something else going on?
Honestly, I'm there scratching my head just like everyone else, because it's staggering to see some of these PPA bids that are coming out. I think it's probably a combination of a few different things. One, the technology costs are coming down very quickly, and I think people, developers, and owners are, when they're bidding those projects in, they're bidding them in assuming a cost curve. So if it's coming online in 2019, they're not using today's prices, or 2020, they're not using today's prices when they're negotiating that PPA. They're really assuming they're being aggressive or bullish on that cost curve coming down. So that's one piece. Certainly there's subsidy support, whether it's the ITC subsidy or some of the other state mandates. I think that's playing a role. And then also, I think there is inherently this first mover desire by some developers, some owners, and utilities, where they want to be a first mover in the space. They're willing to give up maybe some of their return in order to learn how the technology works and what the best use cases are moving forward. So I think a combination of those 3 or 4 different drivers. But yeah, very interesting times. Can't wait to see what the next auctions are going to show for the technologies. It's pretty eye-opening.
Okay, we're about at the top of the hour, so I think we're going to need to wrap it up. Just for those of you who want copies of this, an email will be going out once the presentation and the audio file have been posted. We really appreciate your engagement. Look forward to seeing you at our next webinar, which is going to be on April 19th at 2 p.m., featuring Michael Milligan, previously of NREL, and he'll be talking about a comparison of ancillary services from conventional and renewable power plants. There's also another webinar series that's going on that we are co-sponsoring along with NERC, EPRI, and the North American Generator Forum on the topic of inverter-based resources. And further information on all of these webinars and the meetings I mentioned earlier can be found on the website, esig.energy under events, also in our newsletters and in the informational emails that go out. So, Derek, thank you for your presentation on this webinar. Thank you all for participating, and we look forward to seeing you the next time around. Take care.
Thank you, Charlie.